Happy Friday, everyone. This video is the Instead of Class video for Friday, February 12th, because we canceled class today. Before I get started, I just want to give you a heads up. As I'm recording this video, there's some construction outside of my house. If you hear hammering in the background, do your best to ignore it, and I will do the same. All right, so we'll start this video just with the reminders that you would have gotten in class today. So first thing, we do still have a quiz on Monday. It's just on L'Hôpital's rule, which we have already covered. So it has nothing to do with what we're doing kind of in replacement class today. So if you have not started that web work, or at least have not finished it, make sure you get that web work done over the weekend, just for L'Hôpital's rule. And then the quiz is at the usual time on Monday. And then I'm still chipping away at the exam 1 grades. You should get a grade and some feedback soon. Okay, so we're going to jump right into notes for this section. I'll try to keep this video less than an hour. We'll see how short we can get this video. Okay, so we're starting 6.8, which is improper integration, and I'm saying part A because we're actually going to spend 2 class days in this section. So we'll start talking about improper integration today, and then this is also the content of class on Tuesday. Which is why it's not part of this quiz yet. So we have lots of time to think about it. Okay, so there are 2 types of what's called improper integrals. 2 types of improper integrals, and that's actually how we're going to split up our 2 days. So today we'll talk about one type, on Tuesday we'll talk about the other type. So the type that we'll talk about today is when one of the bounds of integration, so like you're looking at a definite integral. So a definite integral is this form. So without the a and b, it's an indefinite integral. With the numbers a and b, it's definite. So one of your bounds is infinity. So if it's a, the bottom bound would be minus infinity because that's the lowest. Or b would be positive infinity. There's another option as well where both of those things are happening. I want to show you what I mean here. So here's an example of improper integrals of this particular type. This is actually the example that we'll do in a minute. The integral from 1 to infinity of 1 over x squared dx. So what makes this an improper integral, of course, is that this upper bound of integration is infinity. And this means exactly what it looks like it would mean, which is that you are finding the area under this curve from 1 all the way out forever. So in the first quadrant, 1 over x squared looks like this. This graph, right? So let's say this is 1 right here. So if we integrated 1 to 10, we would have the area under this curve up until 10, wherever that is. But if we're going to infinity, we just keep integrating forever. And because of this horizontal asymptote, it gets really, really, really tiny out here. So even though it's technically the area of like an infinite region, that doesn't necessarily mean the area itself is infinity, which is weird for sure. But so the takeaway here is that sometimes these will come out to actually just be infinite area, which is what our intuition tells us would happen all the time. And then other times they'll come out to a number where it adds up so slowly that you really do get a finite total. Okay, so let me give you a couple more examples before we actually compute this guy. So another example of an improper integral of this type would have negative infinity as the bottom bound. And then the top bound is just some other number. Let's say our function here is 1 over x dx. So if we think about visual here, 1 over x does this over here, this over here. Let's say this is negative 3 right there. So the integral negative 3 to infinity is a very similar situation as the picture to the left here. But now we're integrating forever out this way. And it's not clear from the picture whether this would be infinite or finite. We have to do more computing. All right, so the other scenario is what we said was both over here, which is that both of your bounds are the infinities. So you're going forever to the left and forever to the right, and you have to have some function that kind of makes sense for that domain, something like this. This, even though it looks like it should be some massive infinite number, this actually does come out to a finite number. Okay, so let's talk about actually computing one of these. And like I said, we're going to start with this guy right here. All right, so we'll use 1 over x squared as our example. We start here below the picture. All right, so this is an improper integral because the infinity is our top bound here, which means that the definition that we originally had for how to compute a definite integral technically doesn't apply here, right? When we defined like, okay, find your antiderivative, plug in the bounds and subtract, that was for when these were both numbers. So technically this doesn't fit, but we can make it fairly close. So we'll identify the bound that's making this improper, which of course is that infinity right there. And what we'll do is put a letter there instead. So I'm going to leave some space and say, okay, 1, and I'm going to put a B because when it's letters, I use A and B. So use a B up top or an A down below. The choice of letter is not important though. So if you put some other letter there, anything but X would be an okay choice. All right, so everything else is the same. And then I'm going to limit that B to infinity. So instead of actually having an infinity there, I put a letter there and then limit that letter to the infinity. And if I was doing this one, let's say, I would do something very similar. I'd put a bottom letter down here and just limit that letter to negative infinity. This is a different story that we'll get to after. So the next several steps are pretty much a normal definite integral situation. So that limit notation you sort of ignore. And we say, okay, assuming that b is a number, I would find an antiderivative, plug in my bound, subtract. So we're going to do all of that, but there's like a b running around, and then your very last step is to actually assess the limit at the end. So improper integration is a combination of limits and definite integrals. All right, so if I'm going to do an antiderivative, I'm going to remind myself that 1 over x squared is x to the negative 2. And so the power rule applies. So I'll have the limit as b approaches infinity. Again, that just kind of tags along the outside for a while. The antiderivative of x to the negative 2 is 1 over negative 1 x to the negative 1. And that's being evaluated between 1 and b. So this vertical bar is how we keep track of those bounds once we've actually done the integration step. So I'm going to go one more step and clean this up because I'm about to plug numbers into it and it looks kind of gross how it is. So I'll go one more step and just rewrite this as pretty as I can. The best I can make it is negative 1 over x. The brackets that I'm using on the outside are not entirely necessary. I just kind of want to make it clear it's the limit of all this stuff. Okay, so now I'm going to plug in b for x, plug in 1 for x, and then subtract. The limit is still just tagging along, not really doing anything. Extend my paper here because I'm out of space. All right. So this right here definitely becomes a plus 1, right? We have minus and negative 1. But really, it's finally time to evaluate this limit. So your very last step, at least before the computation at the end, is to evaluate the limit as b goes to infinity. So I'm going to put everything else aside and just decide what is the limit as b approaches infinity, negative 1 over b. Remember, because this is a recording, at any time you can pause me if you want to take a little extra time and think. This limit should be 0, right? Constant top, bottom goes to infinity. That whole limit is 0. So I'm going to keep going. I can actually compute 0 plus the 1 from over here. So my answer is just the number 1. So let's kind of scroll back up to the image, right? This was the visual for what we were actually computing down here. So because this came out to 1, that tells us if you integrate this area forever, it actually adds up to 1, which is neat and unexpected, I feel like. All right, so the steps that we did in this problem will be our consistent steps for the most part, right? So wherever your infinity is, you put a letter there and limit that letter to whatever it's supposed to be. It carries down for the next several steps. As you do your antiderivative, you plug in your bounds. Then you finally evaluate the limit and you compute if you can. So you're going to run into 2 possible situations when you do the limit. In this case, this limit existed, right? We got a number and computed. So we'll kind of note for ourselves, if the limit in this part exists, the integral that you're computing comes out to be some sort of finite number at the end, because you can do what we just did here. In that case, we say that integral is convergent. Another way to say that is to say the integral converges, is convergent is another way. And this is defined in the textbook as well, so my definition is not thorough enough for you. You do have another place to look. Now, the other scenario that's possible is that when you get to this step, this limit doesn't exist. So either it equals infinity, negative infinity, or it's something that like oscillates and it's like a DNE for some other reason. So if the limit does not exist, that's my abbreviation for does not exist, the integral that you started with, the improper integral at the beginning, is divergent. So we're kind of defining these 2 words right now. So divergent just means not convergent, it's the opposite. So in that case, you're not going to arrive at a number at the end. If that limit doesn't exist, you stop right there and you say, okay, this integral is divergent, and you stop and that's your answer. All right, so we're going to jump into one more example here. So the example that we're going to do is the second one from the list at the beginning. The integral from negative infinity to -3 of 1 over x dx. Now I encourage you to pause this video right here, try this on your own, and then start playing me again and check your answer. But you're also welcome to just watch it. So for this problem, what makes it improper is the negative infinity as the bottom bound. So my first move, again, is going to put a letter here and then limit that letter to negative infinity instead. Any letter is fine except for x because it's already being used. I usually use a for the bottom bound here, but that's not especially important. So you can see the switch here. I like to do it in a separate color because it comes out extra pretty. So I've just replaced my minus infinity with a and then limited a to minus infinity. The reason that we have to do this is so that we can pretend that a is a number and then everything we know about definite integrals applies, right? With an infinity in that spot, technically definite integrals don't work. All right, so just like in the last example, that limit is just going to carry down for a while I do my antiderivative and plug in my bounds. The antiderivative of 1 over x is the element of the absolute value of x. We're evaluating from a to -3. Notice that this is one of those occasions where the absolute value right here is actually important because we're plugging negative numbers in, and that has to make it okay. I'm going to plug in -3 for x, plug in a for x, subtract. So this right here is just the natural log of 3. which you can leave exactly as the natural log of 3, or you can get a decimal approximation from your calculator. Really what we care about at this moment is the limit here. The limit as a approaches negative infinity of the natural log of a. This is what we need to kind of decide if this exists or not, and that's going to affect our final answer in terms of convergent or divergent, and then if it's convergent, a final number. So this limit is a little bit awkward. One thing you might realize is that because of these absolute values, as a approaches really large negative numbers, it's just the natural log of the positive version of those numbers. So you don't have to rewrite it, but you could also think of it. It would be the exact same thing as this, right? Because these big negative numbers, they're getting absolute value immediately. So it's really just ln of big positive numbers. Now, this limit is easy to decide as long as you know what the graph of ln of x looks like. So I just want to remind you really quick about what that graph looks like. Just the regular ln of x graph does this. So it goes up and out forever over here, and then it has a vertical asymptote on the right side of 0 here. So the limit as a approaches infinity is infinity, right? It just goes up forever. And really, all we care about is that it doesn't exist, right? Equaling infinity is just a special case of DNE. So this limit doesn't exist, which means that we have the second scenario here. So as soon as we decide DNE, we stop. We're not going to compute the rest of the answer. We're just going to say that this integral that we started with is divergent. And that's actually how we answer the question. So when you're answering questions like in the homework or on a quiz for an improper integral, what the directions will probably say is like, okay, here's an improper integral. Decide if it's convergent or divergent, and if it's convergent, compute the number. Right? So you either say convergent and a number, like our first example, or you'll say divergent. Right. So the last thing I want to point out in this video before it gets too long is what you do when both of the bounds are one of the infinities, right? So your bottom bound is negative infinity and your top bound is positive infinity. And we're actually going to use the third example from my list at the beginning of this video, 1 over 1 plus x squared. So you do this kind of the way that you would guess, right, where you have to put a limit in both spots. But there's one important rule to add into that, which is that you have to consider those ends separately. So you have to split it. So for minus infinity to infinity, you have to split in 2. So we're going to say this is the sum of the integral from minus infinity to something plus the integral from that something to infinity. So it's like 2 separate pieces that you have to consider. And then you pretty much just have 2 separate improper integral problems. Where you split it, right, so we have to like pick a number in between to split it, it literally doesn't matter. I usually pick 0 because that's kind of the easiest number to plug into a lot of things. But if you pick 17.5, if you pick pi, it really doesn't matter. You just have to pick some place to split it. So for this one, let's say we choose that 0. I'll have the integral from minus infinity to 0, and then I'll pick up at 0 and keep going. This is generally true, right? If you have any definite integral, you can split it in the middle and just add up the 2 separate areas, and they should add up to the total. So even when the ends are the infinities, this still works. So now we have 2 separate improper integral problems, right? So you need a limit here, a limit here. Two completely separate limits. you'd go from there. So the key here is that if this is going to be convergent, you would need both of these separately to be convergent. So if these both converge and come out to a number, you add those two numbers together at the end, and that's your answer. If either one of these or both comes out to divergent, right, because the limit doesn't exist in a couple of steps, that means that this is divergent overall. All right, so this one I'm going to finish quickly just that you have an answer to this question, and that'll be it. So the antiderivative of 1 over 1 plus x squared is arctan. And I know everyone is dying to do this limit, but it's worth seeing here. We'll have arctan of x from a to 0. Exact same antiderivative over here. 0 to b. So I'm kind of like doing my two improper integral problems like in tandem. So each step I do for both as I go. But you can also just kind of take one all the way to the end, then go to the other one, go all the way to the end. And it should come out the same, obviously. Okay, so I'll plug in my bounds, and then it's finally limit time. So we have arctan of 0 minus arctan of a. Let's see if I can squeeze this in. I'm running out of space. Here we have arctan of b minus arctan of 0. There we go. Squeezed it in. So now we have to think about arctan. This is another one, a lot like the ln graph, where if you know the graph, answering this is a lot easier, but it's not a graph that most people remember. But I want to remind you of what this graph looks like, and then we'll use that to answer all these pieces. All right, so the graph of y equals arctan of x. It has two horizontal asymptotes. The top one is at pi over 2. The bottom one is negative pi over 2. And it kind of squiggles in the middle. So we go up over here, down over here. This is the graph of arctan, just give or take. All right, so as long as we have this picture in front of us, we don't actually need to think about trig at all to do all 4 of these pieces here. So first notice we need arctan of 0 for 2 spots here. The arctan of 0 is 0, right? When I plug in x equals 0, I get 0 here. That's good, that's taken care of. Now, let's do this limit first. This one will be a little bit easier to think about, I think. So the limit as b approaches infinity of arctan of b. That's going to be, where are the y values headed as I plug in numbers bigger and bigger and bigger over here. And you can see from this horizontal asymptote, the y values are getting infinitely close to pi over 2. So this limit exists and equals pi over 2. Now we'll do the other limit. So we have the limit as a approaches negative infinity of arctan. Copying that one right there. So same graph, arctan of a, but now a is approaching negative infinity. So we're plugging in x values over here and looking at the trend in the outputs. So the outputs on this direction are approaching negative pi over 2. This limit is negative pi over 2. If you really, really hate this, you can actually kind of take away some of these facts here and jump straight to the values if you run into this again. So what we just learned was that the arctan of 0 is 0. The limit of arctan in the infinity direction is pi over 2, and in the other direction is negative pi over 2. All right, so because both of these limits existed, I can tell right away that this integral is convergent. And to get its exact value, which I now need, I'll just add up all my stuff. All right, so over here we have 0 minus negative pi over 2. Oh, no, we were adding, sorry. Plus pi over 2 minus 0. Right, so this is positive pi over 2 here, plus another positive pi over 2 here. And I have just enough space to write my final answer. My final answer is pi. So if you integrate the area under this entire graph, forever to the left and forever to the right, it will add up to exactly pi. Okay, so we're going to stop this video here. Like I said, we'll continue this conversation in class on Tuesday. If you'd like to see some more examples done, there is also a video in the week 5 folder with improper integration part A. You can see me doing a couple more examples